Really an honor. All right. So, as you just heard, Stefan Pabst and I are both at Relational AI. Uh, we are still fairly young startup developing a brand new relational knowledge graph database platform. And so I'm going to be speaking a little bit about that platform. Uh, and also about what we can build on top, how we can use it as a tool for building intelligent data apps in RHEL using reasoning and probabilistic modeling. And probably already there's one term up here you haven't heard before. The language RHEL is a declarative database language that is the tool that allows us to do the reasoning and probabilistic modeling really in database. So we're going to be covering a lot of that in this talk. So first, a little bit more about our company. Relational AI was founded in 2017 as a from first principles cloud native platform. We're recently out of stealth with our first enterprise customers. We are really a strongly mission driven team. We have a strong concept of a very new kind of product, and I hope to introduce you to that today. Um, uh, we also have a very active board of directors, a lot of people behind us who are very passionate about seeing this product succeed. So it's a very exciting time for us to be involved. I won't go into this full slide, but we're HQ'd in Berkeley. We've been fully remote from the start, so it's a wonderful collaborative atmosphere that happens mostly online, and so we are in the cloud ourselves, so to speak. We have over 50 PhDs at Relational, 2,000 plus publications, 100K plus citations, 37 awards and counting. So we've always kept very close to our academic roots, and I think you'll see that today. So first of all, what we are building at Relational AI. As I said, it's a cloud native relational database platform designed for structured and semi-structured dynamic data, and with the data and application logic together in one place. So this is basically my outline. This is where we're going to start. Is what do I mean by these three things? And this is almost the full outline. So then we're going to have some fun and get into examples of intelligent data applications built on the ArcHMS with the language RHEL, and we're going to talk a little bit about the future of what intelligent databases are and what we see them looking like. But let's start here. Let's start with what motivates us. So we are a cloud native relational database platform. And talk a little bit about the motivation for building this thing, and a little bit about how it's architected. So first of all, our motivation. This drawing here is supposed to represent something like the modern data stack. Okay, what makes it really modern is that you have this cloud data platform. I don't know if folks can see my mouse when I do this. I think so. So a cloud data platform at its core that is able to separate data from engines, so from compute power. You can scale up and scale out as needed for the application at hand. And now, for the first time, all of your data apps, your BI tools, everything that would traditionally have its own small database, specialized database, can now access the broad swath of data available, with one source of truth, so in one location. And this is very powerful. So now your data apps are communicating with the same source data at the same ground truth, and you can sort of build on top of that. This is great, but there are some division here that makes the process not quite smooth. So you have data apps, you have ML tools, you have BI tools that are written a very procedural or navigational, like a graph database kind of way, or procedural calculation kind of way, versus your database, which is declarative. To date, these applications, these other tools, which contain all of the logic that's related to your data, are not cloud native, so they don't scale out the same way that the underlying data does. So you can't work at the same scale that your data really is, and you miss out on things because of that, on insights. There's also other advantages that you get from the cloud data platform side that don't translate into the application. So, data sharing, versioning, time travel, zero copy cloning, these advantages where you can really iterate on your data in the database, but not in the logic layer. So what we see our platform doing is complementing the cloud data platforms that are out there now. Doesn't really matter which one; they all offer very similar features, and we extend those to new workloads, right? So we bring in more data science, more data applications. We bring in graph analytics, JSON analytics. Relational application logic, so knowledge and semantics in the database, predictive and prescriptive analytics, all of that can now, with our platform, be brought into the cloud native layer and be done at scale. And key to achieving these new workloads is this idea of having a semantic layer, a semantic model built on top of the database. Okay, so now instead of just directly integrating with your data in a set of tables in the cloud, you have some reasoning model attached on top, some way of contextualizing your data that is also a single source of truth across data apps. So let me explain a little bit more what I mean by that. Okay, so we have the semantic reasoning and semantic model layer on top of the data. Um, this also shares the advantages of the data sharing, the versioning, the time travel, zero copy cloning. But what is it? I'm going to explain it through an example, and this is an example that's going to show up over the course of our little mini lecture here. It's a flight data, it's intelligent data app. Okay, and the applications for such an app might be something like tracking performance of carriers, airports, aircraft models, individual aircraft. You can discover relationships between seasons or time of day and weather delays, planning and optimization of routes, looking at historical trends. If it's live, you can act on the issues as they're arising. So this is sort of the sort of environment we're going to contextualize our introduction to the system around this flight data application. Now let's look at how this kind of data would look in a traditional SQL database, right? So you have tables such as this one that talk about the flight details about the flights, carriers, origin, destination, but quickly you see that you're missing context, right? So what is the primary key for this table? When I'm given data like this, a flight time, is this hours? Is this minutes? What is this? Um, it turns out this data set includes helicopters, but that's not at all clear from just looking at the flight numbers and the origins destinations. You might be messing up aggregates if they're coming from your raw data. What does this mean for there to be a flight time of 0? Is that going to be correct if you start aggregating across data? Some things are in columns that don't really apply. So you have an arrival delay that's negative. That's not really a delay. How is that going to affect your calculations? Again, periods that don't have any units attached to them. Um, are certain data points exclusive Boolean values? Canceled, diverted? Are these exclusive? What does this mean? What are the possible values? So you lose out on this context without that semantic layer on top. So we're gonna go back to this example later and add that in and show what that is going to look like. Right now, this reasoning layer is now implemented procedurally, right? So you'll have this in your data app on top in languages like Java, C Sharp, Python, etc. And you end up with this sort of split brain problem, right? Where the data is managed in one layer and the knowledge and semantics are really separated from that. So fixing that will have a huge impact. It'll bring the app logic to the data, right? And with one single source of truth, and you'll be able to do it at scale across your entire data and derive insights across that full scope of your data. So in order to build this new platform, we had a few core requirements. Those are, first of all, scalability. You've got to separate data storage from compute. You have to be able to scale out the compute as needed for the application. data independence. So we want to separate the application logic from how it's represented from the data representation. But we also want to keep the two side by side. So data and application logic together in one database in order to achieve semantic reasoning. We also want this to be performant, so we want to have a live programming environment. So we need to be able to support things like incremental changes to data and logic. There are 6 key innovations that are behind our product. It's a lot to cover, and we absolutely will not be covering it all in this lecture. Um, I'm actually going to touch on several of them, and Stefan will as well. So you'll be seeing versions of this slide again show up when I say, we're coming back to this. But we're not going to do a deep dive into these core innovations. What we're going to be focused on today is what we can achieve with them, right? So having these things in place, what do they allow us to do? That and allows us to do for data apps. So that's the focus of this lecture. But if you want to learn more about the system, I am going to throw this up here. Please take a screenshot and in your own time check out some of these lectures. So learning more about the modern data stack, and how relational knowledge graphs fit into that. There's a nice talk by Bob Mulia on our board. Our VP of engineering, Martin, gave a series of 2 great talks that really complement each other going into the RAI system. So the ArcGMS and how it works. So these 2 complement each other well. I recommend them in this order. So the CMU relational AI talk, if you Google that or YouTube search that, it'll come up. And then this second talk, the DSDSD database seminar on algorithms for relational knowledge graphs. So both of these are excellent resources. Okay, so that's what motivates us. That's what we're trying to build and what we're trying to achieve. Let's talk a little bit briefly about how the system's actually architected. So the architecture of the database platform is really related to scalability, right? So that at its core, separating data storage from compute, so that we can scale out our to whatever scale is necessary for the data at hand, right? Uh, so you have layers that look something like this. You can do your app development in whatever resource you like, and then via that resource, you're going to talk to the ArcGMS through a RAI SDK. These are written currently in Python, Julia, JS. I think we have a Next.js as well, Go, Java, C Sharp, growing list of languages for the RAI SDK. You can sort of pick your poison there. Hi, there we go. And in the cloud region, that's where you communicate via our services to a provisioned engine, and the data itself lives in another layer in like durable object storage, like S3 or some bucket. Um, and and in this way, you can really provision engines and even have a serverless engine environment. The sort of plugs are in place for that as needed to scale your solution. So the architecture here touches on one of these key innovations, immutability. This is really critical for our data storage, that it's the data and metadata are versioned and immutable. I'm not going to get into this, but I wanted to call it out. And I wanted to also flash another slide up here. This is sort of a list of our influences and resources that are related to how we architect our storage management. And if this is a subject that's interesting you, please take a screenshot and check out these resources. So as far as how you communicate with the ArcGMS, I think in this talk we're going to focus mostly on the language REL, which is a relational database language designed for semantic reasoning, designed for advanced application logic that we've designed to fill that gap in having a truly declarative relational language that handles these workloads. But it's not the only choice. So if for those more comfortable in SQL, there's SQL support. You can fully talk to the ArcGMS via SQL. We also support other semantic languages like Legend, and we have plans for more in the future. feature language support. The data formats that we take in, currently we handle structured data via CSVs and semi-structured JSON. We have a couple other formats that we're supporting and many more on the horizon there. The intermediate representation is a rel representation. That's how the data lives inside the ArcHMS and how it's the layer on top of which we construct all of our query optimization and logic and execution innovations on top of this. And then at the core is what you saw before, the relational knowledge graph system architecture. So just quickly to kind of walk through the steps of how a transaction is executed. You have your rel model or your SQL query on top. This is parsed. We go through a dependency analysis and a type inference phase. We do specialization to first order logic, then a dependency analysis, semantic optimization, physical optimization, and then evaluation, either vectorized and we have just-in-time evaluation. The stages that it goes through depend a bit on how the optimizer and the various other layers handle the data. And each of these layers talks to a metadata database built on Salsa and Julia. And this is sort of our tool and our for maintaining incrementality in a live programming environment. I believe Salsa has now been open source too, as well. So that's available in the Julia environment. Okay, so we've gotten through our first outline bullet point already, and look at the time. Still so far to go. So we're building a cloud native relational data platform, and hopefully you have some idea of what that means now. So on to what it's designed to do. So it's designed for structured and semi-structured data. So I'm going to talk a little bit about how we implement that. So first of all, what the relational model is and the paradigm and why we value it. Then we're talking about in practice what views on relations look like, and then we'll talk about the performance implications of our implementation. So first of all, the relational model. Just want to really emphasize here. So the relational model represents all data using first order relations, okay? The purpose is to really have independence of application logic from changes in data representation, right? So this data independence is the central goal here, and it's what the relational model was designed to achieve. I want to call out that SQL is not the relational model, right? This is one implementation of the relational model. And I call this out explicitly because the inadequacies of SQL are often used as motivation for some totally new data models. And it's really the relational paradigm is sound. It is really that we need to go beyond SQL in the implementation to get the other features that we need. So again, back to our core requirements, the slide will be flashing up a few times. Data independence is really a core requirement. We want to be able to support changes in our data, additional data, new streams of data, and not have our application logic need to be rewritten to accommodate that, right? So the application logic should be a layer on top and not depend on the data streams that are being represented. So we achieve data independence with RAI relations. All data and logic is stored as RAI relations. So both data and logic are stored in the form of relations. The application logic, yeah, I think these points say the same thing. Application logic is also written as declarative relations. It's relations all the way down. It's turtles all the way down. Tables and graphs, etc., are composed views over those relations. So what is a RAI relation? Well, they're not tables. Relations you can think of more as the building blocks. They're the Legos. They're the basic unit you construct your views out of, right? So they're the building blocks of tables, but they also enable many other views on data, graph, JSON, RDF, etc. relations are narrow. So I'm going back now to that flight example. Here's a sort of miniature version of a flight table where we have carrier, flight number, origin, destination, and departure. So rather than store the data in this wide table view, we break it apart into narrow views on the data. So for each key, table key, we have, for instance, the departure information. And we do this for all of the data. For those who know, this is called sixth normal form, right? So Rye relations are in sixth normal form. Really just these key value pairs, single valued pairs for each key. And what does this narrow data structure allow us to do? So the advantages are that they're extensible and dynamic. You can add base data, for instance, new base data. You can add derived logic on the data without touching your original relations. You're not tables anymore, but your relations, if you will. You don't need to touch them to add logic on top. Um, you're free from nulls. In this representation, the data is either there or it isn't. We do still support missing. That's different. But we don't have to be a slave to nulls anymore. We can escape that. And also they're composable. So by building with these Lego bricks, with these relational elements, we can create tables, subgraphs, and other views on our data. Okay, so what do views on relations actually look like? A table we've already kind of seen. So the composition of a table is sort of the opposite of what we just did of breaking it apart. A table view is composed of a module of relations, all that share the same keys. A module is a rel concept that's basically a relation of relations. Okay, so we can group relations together under a single umbrella as a single relation. It's still relations all the way down. And in our flight example, you might visualize this way, right? So we have some table view that represents flight. And within that flight relation are a set of relations that might correspond to a table column. Okay. And the let's see here. The way that we would query this is really just as though that semantic data um, the individual columns in a table view, if you will, are just part of our key, right? So we had this example of a carrier here for this flight. It's Alaska Airlines, I believe that's AL. And if we put this under the module of a flight table, we would just simply query it this way. So we want the carrier. Here's the flight. Here's the value. You could see the analogy here with the table view, right? So this relation flight has some relation within a carrier. This is similar to a column, and we have this key, which is similar to a table row, and our single value. We can also represent graphs as a view. So a graph view is composed of a set of GNF relations. So I'm going to explain in a second what GNF is. You've seen 6NF, so now we're going to talk about GNF, graph normal form. So going back to our exploded view of our flight table, so this is a set of relations that comprise our flight data. You can see immediately the analogy here with a graph. So each of these binary relations, tuples in this relation, are equivalent to data about an edge, right? So here we're connecting flights to their origin, their airport origin. Um, Here we're connecting them to their destination, departure connected to a time, flight number, carrier, and so on. We can visualize these as a graph. So here they are sort of set up as a graph. Where now we have these flight nodes with many outgoing edges that are connecting them to various data points, right? I think I have the arrows here the wrong way, but you get the idea. The only thing that we're missing is the things and not strings. All right. So this is critical for a graph. You don't simply want to connect contextless data. You need to add that context there, that semantic meaning. That's what we call the graph normal form. Okay. So what does this mean in practice? This means in practice that we need annotated data. We need to know that AL can have the type of a carrier. All right, because you might imagine that AL could also be the code for a airport or some other kind of data. You want to distinguish these concepts, right? So we do that by introducing this idea of graph normal form and things not strings. And now we have separate concepts in place for locations, for times, for flight numbers, and for carriers in this case. So here is a schema view of that graph I just showed you. So rather than showing each individual node, I'm now showing the sort of schema level. So here's this concept of a flight that we are representing as numbers here. Airports here in green, the date times for the departures and arrivals and so on, flight numbers and as integers here, and then the carrier, the airline as well. How do we get to things from our strings? We have two ways of doing that in Rye. So first of all, what is a thing? A thing, as I said, is it's this annotated data, right, that adds the semantic context that you're missing. We do this in two ways. We can do this with what we call value types. So with a value type, you can go from data that's represented, say, as an integer, to declaring a value type called flight number, for instance. And now all of those numbers that were in there as simply integers now have a data type that's very explicit to what it means, right? So it's a flight number. And as you'll see later, when we build that logic layer on top, we can write relations that only ingest flight numbers, right? So it'll only return values over flight numbers, as an example. So you can use those custom types value types that you've created in your logic. We also support entity types. So for example, in this case, a flight we've been just showing as integers before, but this isn't very robust, right? So if you bring in new data and you need to kind of keep track of a number that doesn't really have any context, this can be very tricky. So what we want is we want to define a flight by the characteristics that make it unique, right? So what is the real primary key of that table? We can define that by just telling the system what are the important unique identifying features. So in this case, the carrier, right, and the flight number, but also the day it departs. You might have the same carrier with the same flight daily, for instance. But with this combination, you come at a unique representation for what a flight is and a unique key for flights in your graph. So that's the important element that we need to add to get to graphs, is this idea of things, not strings. And these are the tools that we have to do it. So here you're seeing it in a sort of pictorial form, and later we're going to show it as code. So relational modding is literally a natural fit for graphs. I think if you take away just one or two things from this talk, I hope this is one of them, that the relational paradigm is really uh, ideally suited for graph and for graph applications. Just as a little aside here, so you might be more familiar, if you're familiar with graphs, seeing them as labeled property graphs. So this is a kind of graph where you can actually have properties on top of nodes and on top of edges. So in this case, the actor node has a name attribute associated with them. This acted edge also has an attribute, this role that the actor played. We can also represent this with the relational modeling. Okay, so we can represent nodes as these arity one or unary relations with the node identifiers. We can represent edges, as I already showed you, with the binary relations. So here, the connection between a node and its attributes is just the same as any other edge, right? It's just going to be a leaf edge. Yeah, and so we can do this for all of the various nodes. We can also connect the nodes. So here, the directed and acted edges connect node to node. And we can also define edge attributes, and we can do that via hyperedges. So this is not really uh, kosher with a labeled property graph diagram as it's shown here, but it's no problem with a relational model, right? So we can simply connect, in this case, this actor node, node 1, with the movie node, node 3, Dune, and up and add the role. So here that he played this character, Paul, and I'm not going to try and pronounce that last name. I haven't seen Dune yet. Paul Atreides. Uh, okay, so that's graphs. Onward. So we don't just have the ability to ingest structured data, right? We can also ingest semi-structured data. We support JSON, for instance, and JSON analytics. So JSON in the Riot platform is a view composed of modularized relations. So it's a little bit similar to a table. So let's see how that actually looks in practice. So in Rye, we represent JSON again as a series of first order relations. They're in graph normal form. And the way we can sort of get there is by imagining, the JSON as a tree, right? It's typically represented as a tree after parsing. Okay, so here for this idea of a JSON data representing a contact, we can break it down as a tree like this. Okay. So let's recompose this tree more in a relational kind of look. In this case, the green cells here are the internal nodes of the tree, and the gray cells are the leaves, right? So that's the actual data. We break this up, and immediately you can see what this looks like as a set of relations, okay? So the green prefixes, again, become the keys to the data, right? So for each row here, each tuple, you have a set of green keys, and then you have single valued data. So we're in 6 normal form, and each of these is unique, and so it's really achieves this graph normal form. You could break these out, right? This is the same way we were talking about with tables. So we actually specialize. We call it specialization. The keys as relations themselves. Okay, so this allows us to distinguish schema from data, and it helps as we evaluate. So it helps us performance wise to distinguish these as separate relations. We also do we maintain sort of an internal physical representation that we do some reordering on to really distinguish the schema side and the metadata side from the data side. So here I'm showing you the internal sort of physical representation of phone numbers where we've reordered this list information into the data. But this doesn't actually impact anything that the user would experience. So you still query via the logical representation. You would still sort of use this key order to access your data. So it'll feel very much like a JSON document. And generally what we recommend is once you've ingested your JSON in this form, the next step is really doing some schema mapping on top, right? So breaking out this data into GNF relations, into narrow GNF relations, single key. So I've shown you now how we can use the relational model and use what we call these Rye relations, these 6 normal form, graph normal form relations to compose many different views of our data, to ingest structured and semi-structured data. And that this allows us to achieve data independence, where we can extend our data, we can add to our data, and our application logic is allowed to just sort of sit freely on top of that, and it doesn't need to expect any sort of changes to table structures or things like that. If narrow relations, though, are so great, why aren't they the standard already? Why doesn't SQL work this way? And the answer is simple. It's performance. Joins are hard. So let's talk a little bit about why joins are hard and how we make them less hard, right? So how we are able to actually do this. So this is hitting on performance, okay? And actually this hits on 2 of our key innovations. So join algorithms, the algorithms that we implement, these newer algorithms that allow us to achieve the performance that we need, and also the details of the implementation. So being able to compile complex joins down a native code using a vectorized engine for simpler joins, making that decision about when to do those cases is a system innovation that I actually won't get into right now, but I do want to spend at least a few minutes talking about join algorithms. All right. So knowledge graphs, they need different join algorithms. They need join algorithms that are different from the standard SQL-based algorithms. So in a SQL-based relational database, typically the algorithms are binary join algorithms, okay? But for knowledge graphs, the intermediate results that these binary algorithms will produce are just too large. So let me go through an example of that. Okay, so let's say we have a query where we want to find a child who acted in a movie that was directed by their parent. Let's call out some nepotism here. So we have three edges that are at play: directed, the relationship between the director and the movie. We have child, the relationship between the director or parent in general, person, um, and the actor itself themselves, and acted in. So an actor that actually plays a role in a movie. Okay, and you can see that this is a sort of triangle graph pattern here. Any of the binary joins that we might choose to do sequentially for a typical binary join algorithm are going to be awful. So you can imagine we join on directed and child. Well, that's not selective. Most directors have children. Okay, so then we select directed and acted in. Okay, well that's not selective. Every movie has a director and has actors. Okay, again, the child relationship and acted in. It's not selective. Really, every child has parents. Okay, and so this is one of the many reasons that that you have this stigma that joins are bad. Okay, and why in SQL you do as much sort of pre-joining as possible in constructing these tables. Um, so we get around this with a set of worst case optimal join algorithms. These are a new class of algorithms. A lot of their properties and trade-offs are not yet fully understood. So it's very interesting to be at the forefront of these technologies and these techniques. We implement the leapfrog tri-join, generic join, dovetail join. Those are some of the um, worst case optimal join algorithms that we implement. Um, and we sort of look at their properties from three angles. Okay, so first of all, the benefit of one of these algorithms is that they exploit the sparsity in the data. So they actually take advantage of that to achieve performance. We also look at recasting the subquery problem, and we embrace correlation. So I'll talk about that in a minute. And we also recast the index selection problem. So I'm gonna cover these at sort of a high level, and that slide I showed you before with other talks kind of dives deeper in if this is interesting to you. Okay, so let's talk about sparsity. All right, so we're going to construct a query where we look for a female Asian director that is an Oscar winner. Okay, it turns out there's one, so very sparse data. Um, so first we can seek for female, and we can seek across Asian, and we see that there's big gaps here, right? So this allows us to, if could do this with the worst case optimal join algorithm, to do this together and to make fewer hops because we're hopping across these gaps. Okay, and again, not going to go into the details, but you can see, at least in this case, we only do really 7 hops before we land on that one solution. Okay, so they use this sparsity in each of the relations to narrow down the overall search. Okay, now the subquery problem. All right, so there's two really undesirable approaches to handle subqueries, right? SQL systems will attempt to rewrite and decorrelate to avoid these. And the first approach is top down, right? So you imagine that for each row in your main query, you execute the subquery. But this could really be time consuming, right? And then the bottom up, you overcompute, right? So you compute the subquery for everything, and then sort of filter with the outer query. But this is also potentially going to blow up on you, right? So we address subqueries with two powerful and general methods. The first is we identify uncorrelated subqueries with the semantic optimizer and handle those. So this is something we'll talk about in more detail later in the talk, but it comes up here. We also embrace the correlations. So when there is correlations, we can use worst case optimal joins as a sort of correlated join device, right? As I showed you before. So we also recast the index selection problem. So index selection to auto tuning, this is an open and unsolved problem. All right, but we decided from the very start we don't want users to have to deal with it. Okay, they should not have to be asked to manually define indexes or supervise, tuning approaches, anything like that. So we want this to feel very just auto magical. So you declare what you want, and the system does what it needs to do. So in order to achieve this, everything is an index in our graph-like schemas. So you can compare this with RDF triple stores that create indexes for all orderings, or SQL tables. They store an index for every functional dependency. All right, but we store an index for everything. And with these worst case optimal joins, it's a device where we can create these composite indexes on the fly, and we can do it cheaply without affecting the performance. So what does that look like? So creating these indices. So for example, I have a mini graph here where we have a connection between cars. I'm representing those numerically with their brand and with their model. So here we have one car that's a Ford Escape. We have another car here that's a Jeep Cherokee. If we think of this as our relation in our relational building blocks, we have relations like these, right? And we decompose these into our index building blocks. So really every permutation. So key, value, value, key, and so on for both brand and model relations. And then we can break these up into every combination of index and do this without sorting. So this is what what these algorithms allow us to have access to as needed. If you're interested in join algorithms and want to learn more about the join algorithms that at a deeper level, the join algorithms that we uh, employ, check out these papers. These are our sort of influences, the influential papers that motivated us. And keep it up for a sec for grabbing a screenshot. Okay. Okay, so now we're getting to data and application logic together in one place. We've covered what we're building, a cloud-native relational data platform. We've talked about that it's designed for structured and semi-structured dynamic data, and that it brings the data and application logic really together in one place. That's what we're going to cover now. And I think I'm doing well on time. So I think I'm able to continue. But maybe before we dive into this section, I can take a very brief pause. Is there anything that questions folks have, or anything anyone wants to talk about before I continue? We've been going hard for 47 minutes, and I thought this would take at least an hour. So that tells me I'm speaking a little quickly. So I want to make sure that I'm not rushing you along here. But
I
okay.
am not sure if the participants are allowed to.
Oh, okay. All right. No, that's fine then.
I'm not sure. I mean, Kumar, are you there? I guess they can ask
Yes.
directly.
All right.
Yes, I am there.
Oh, okay.
Yes, I
All
am
right.
here.
Okay, so everybody can use the microphone here to pose a question, not necessarily on the chat. That's why.
Okay.
All
All
right.
right.
Okay, if someone wants to ask a question, I mean, it's maybe a good time to ask a question.
Yeah.
Ask.
Let's see. If not, we'll forge ahead. There we go. All right, onwards and upward. So we've covered that what we're building. So this cloud native relational database platform, it's designed for structured and semi-structured dynamic data, and I hope I've sort of illustrated that for you. And now we're going to talk about application logic. So we're going to store our data and application logic really together in one place. Okay. And what does that look like? So this is all around our core requirement of supporting semantic reasoning, okay? That we have one source of truth for also our semantic layer on top of our data, okay? So I'm going to break this section up into really four sections. So we're going to talk a bit about the semantic layer, a little bit more on what we mean by that. Then we're going to introduce the REL language. Um, and then we're going to get back to our flight application example and talk about that as a use case with really bringing in that application logic into the data. And then we're going to talk a bit more about performance. So the tools that allow us to do this in a performant way. Okay, but first the semantic layer. So you've already seen this slide. Part of our proposition is that we really want to make the semantic understanding of the data part of the database. So where those two things are tied together and really that you attach the semantic meaning directly to your data rather than having it sit separately in separate data apps, right? And you can see how this might be a risk when your application logic is really separated from your data, right? So you can imagine having definitions, for instance, of concepts that might be different across different apps and across different sort of access points, and this can lead to data confusion. You also aren't able to really build logic across your full set of data, your sort of that cloud scale terabyte plus data, because you just can't really do that in apps that aren't cloud native. Okay, so by bringing this sort of reasoning into the data the database, you're able to achieve these things. Okay, so there's various approaches out there to semantic modeling. Some of them are SQL based. So, for instance, DBT very recently announced that they want to tackle a SQL based approach with the latest round of funding. Their big sell is they want to tackle a SQL based approach to building that semantic layer, right? Malloy, Google and Looker, it's a proposal to succeed Look ML and maps to SQL. There's open industry-based solutions out there. So Legend by Goldman Sachs. This is a UML plus OCL kind of inspired approach. It also runs on SQL. We also support Legend actually, so you can put the Legend semantic layer on top of Rye as well. So Morpheer is another approach by Morgan Stanley. So this is a functional programming based approach, and it runs on Spark. And then there's certain sort of just standard based, of course, approaches. So the SBVR, semantic business vocabulary and rules, and the semantic web, of course. So this is the W3C standard, Sparkle, RDF, OWL, Shackle, all those. And so you can see that the it's a timely sort of interest across the board to bring the semantic modeling to the data, and what the way that we think of it is that we really need to really redesign this from the ground up, really with breaking free of the SQL mold, so that we can do this in a performant way. The semantic layer is so let's go through an example. Let's go through an example to talk about what the semantic layer really is. Going back to our flight tracking database. Okay, so let's think about some example functionality that we might want to have. All right, so for example, how many transfers would I need to travel between two cities? Maybe I want to ask that question. What percentage of flights were delayed this year per airline? Okay. If a percentage of flights arrive delayed to an airport per day, should I, can I send an alert? Can I trigger off of events? The system can't answer these questions if they don't know what these concepts mean. So this concept of delay, this concept of transfer, what are they, right? So we want to build that application layer that defines these things, and we want to bring it into the database and have it really uh, uh, dynamically um, populate these concepts as our data changes and updates. Okay, on demand. We want to be able to do this on demand. Um, so let's answer some of these questions, right? So we can define what a canceled flight is. This is for a flight, and if it has a certain field as marked yes in our data, then this flight canceled edge leads to yes, then that means that it's canceled. So we can define a subset of flights that are canceled. We can do similar for diverted. It also comes from our source of truth data. We can also impose requirements. We can complete this triad of statuses for flights by saying a flight is marked arrived if it's a flight and it's not canceled and it's not diverted, right? So this is purely coming from the logic. This is the layer. This is really a layer on top. So this isn't defined anywhere in our source data, but we create this concept and populate it based on the logic of our data. Okay. We can also contextualize sort of the data with values. So the arrival delay, um, it's going to be a maximum of 0. So those negative delays aren't really delays, so we're not going to populate from those. And if it's a positive delay, then we're going to take it from our data here, and we're going to give it the type of minute. Okay. We can ask questions over these well-defined concepts. We can count, for instance, canceled flights. Um, we can find the mean of arrival delay and find out the mean arrival delay. We can do the same thing by carrier. So for each carrier, give me that mean arrival delay. Okay, and we do this in a declarative way. So we tell it what we want it to return, and it does it for us. Uh, Calculation. All right, so we've already sort of introduced an example of the RHEL language in this case here. So all of this is RHEL, but now we're going to dig a little deeper into the RHEL language and what the capabilities are. So this is again one of our key innovations. Coming back to this slide, and this is the one that we're going to explore in the most detail in this talk. So RHEL in a nutshell. RHEL is designed to handle. Is designed for semantic modeling and querying. It's designed to express complex business logic. It's able to handle structured and semi-structured data, as you've already seen. It's a natural fit for graph use cases because it promotes this graph normal form. It's readable for business users. I hope you'll see that. It's fairly easy for developers to pick up. It's also very expressive. It's quite concise and extensible. So Datalog. Datalog is a great foundation. And actually, you could think of Datalog as the internal representation, the intermediate representation for RHEL. So the good about Datalog, it has an outstanding formal foundation. Um, supports mutually recursive definitions, but more is needed. Datalog's not enough, right? So classic Datalog, so globally stratified, is really too limited for graph workloads. You can't do value creation, aggregation, negation, and recursion. And these are really required to do graph analytics. Datalog does not support abstraction. So this is similar to SQL, Cypher, Sparkle, etc. You want to be able to abstract over concrete relations and especially abstract over schema. So we'll show you how we can achieve this in RHEL. We can do this in RHEL. So here is what a relation at its core looks like. You have a relation definition. It has some key and it has a single value. So data and logic are both organized with relations. Okay. You have declarative logic, right? So this first order logic, really based on Datalog as the sort of spiritual founder. It's a principled way to express data manipulations and queries. So here we have an example of inserting some data. We're inserting into this parent relation from load CSV. Here's an example of inserting logic, or sorry, installing logic. So you can define a concept like a grandparent. And here, this grandparent exists if for a person YZ, if the parent of X is Y and the parent of Y is Z. So then you have this X as a grandparent. Rel supports abstraction. So there's a concise expression of knowledge. You could express paths naturally, right? So here is a recursive example of how you can define reachable using this dot or composition syntax. Um, we support higher order logic, so expressing complex business logic is reusable components. So here I've created two definitions: the mean, which is over some relation, so I can pass in this higher order relation and do the sum over it and the count over it and return the mean. Similarly with the argmax, I can return the using that composition syntax, I can return the argmax. We support recursion. So this is critical for expressing complex business logic. And we support non-stratified logic. So that means we support negation, we support aggregation. Here's an example of that. This is the PageRank algorithm in RHEL. So you can see that we have our sort of base definition here, and then our recursive definition on top, which actually, oh, I can't click on that, which actually invokes PageRank. Um, and does a sum as well. So you can see that this is this non-stratified logic here. We support integrity constraints. So you can declare integrity constraints and validate and enforce logical consistency of your data, right? So you can declare that data can be, for example, transitive, right? Here's an integrity constraint checking that the transitive property. You can check that certain uh, people or objects are older, and this should imply that, so for in this case, that if person one is older than person two and person two is older than person three, then it should be that person one is older than person three, right? So logic like this. You can enforce functional dependencies. You can enforce types. So here we're ensuring that if a value is in a relation, then it's a string. Okay, um, you can enforce things like this. Modules you've already been introduced to more in a sort of pictorial representation. Here's what modules look like in RHEL. So these are an organization of application logic. It's a relation of relations. And what modules enable, they enable also an ecosystem of libraries. So if you combine these with higher order relations, now you can imagine having libraries where you pass in relations and can do have reusable sort of logic over those relations. You can also have custom modules that you can query. So for instance, here I have some sample data and I want to get some stats out of it. So I calculate the average over the data. So here's the higher order relation average. I calculate the sum over the data, and I can gather these together in a module about my data, and then query it like as such. So here I'm querying stats and this relation my average. I could also write this, using brackets and sort of treating my average as a key. So the sort of way of thinking about these feels very natural, and the way of sort of querying into relations and into modules feels very much like querying keys and values. I can do schema abstraction. So schema and data are both first-class citizens. As you saw the example here that I'm treating sort of, I can treat my my relation as a key itself. I can do that here to pull out schema information. So here I have some relation, unary relation in a graph module, say called stats. I have some node names, and I want to pull out, or no, here I'm using this example, I think. So you could do this also for graphs. So let's say for my module stats, right? I want to know what are the relations that are inside my module stats. So I query out, okay, stats. I have the name. In this case, this example, I was querying out my average.
It seems to have lost Cassie.
Same problem here.
Then I'll come back to this. Thank you. Okay, so onwards with the rel key aspects. So um, you've already seen modules. I've already introduced this sort of in a pictorial way, but now I'm going to present it in rel, what it really looks like in rel. So modules allow you to organize your application logic, right? So you can treat it sort of as a way to create namespaces. It's more than that, but that's sort of one way of thinking about it. Um, and what modules can enable then is really an ecosystem of libraries. So if you combine modules with higher order logic, now you can imagine a set of reusable relations where you can pass in other full relations and do, or multiple, and do computations over them. Okay, so this is how we construct our standard library. So our standard library is rel is written in rel. So we have a set of standard library relations. You saw an example here before where we have the definition of mean and argmax, right, are written in rel. So we can support libraries of these using modules. You can also support custom modules that allow you to sort of delineate your application logic. So here I'm showing a toy example where I have some data, right? And I define a module stats, which gives me some aggregations over that data. Okay, so here I have my average. It's a relation that computes the average, and my sum, a relation that computes the sum. Okay, and the way that I would query this is I would query it just the same as I would a set of keys for relation stats, right? So here I could have put these square brackets around here, but you can leave them off in rel. And so here I'm querying just the relation my average inside of the module stats. Okay. We can also, because we sort of set things up to treat schema and data on equal footing. So here again, it's both. I'm able to query in as sort of like as a key the relations. You could do that. You can use that as a tool to do schema abstraction. Okay, so let me show an example of that. So here I'm wanting to pull schema information about my module stats. So I say, okay, for stats, pull out all of the relation names. Okay, and I don't care about their value, but pull out the names, as long as that name is not my average. Okay, so give me everything else that stats has. And if I query this, what I'll get out is I'll get out my average. Excuse me, or sorry, my sum. I'll get out my sum. So now I can see what are the relations that are in my module. So I've just done a sort of query over my schema. And I did it the exact same way I would have done it had name not been a relation, but been some sort of data in a binary relation stats. Okay. So really there's this equal treatment of schema and data, which allows us to do this so easily. All right, so then onward to schemaless modeling. So schemaless modeling uh, is related to our support for sort of overloading relations. Okay, so we can focus on the application logic and not really on the particular schema, at least in the front end. Okay, but still in the back end, we support a type stable database. Okay, so let me show you a little example of that. Example. Here I've created a definition for pi. I've created it using many different types. So here I have a string, here I have a single character, integer, float, decimal, fixed decimal, irrational. These are all numeric and string types that we support in rel. And I've overloaded this definition. So if I were to query this, if I were to just look at it in the logical view, I would see a single relation with mixed types, right? So I have characters, I have the strings, I have my different data types, okay, my different numeric types. But in the back end, in the physical view, what's really happened is that we've now separated these out into separate relations. So I have one string relation pi, I have one character relation pi. I have a rational and so on, definitions of pi. And by having this separated out, I can then write other logic that maybe only pulls one or the other, that only pulls matching types, for instance, so that I can do rational, let's say, algebra or I could do floating point algebra, depending on the the application logic. But I don't need to worry about it with pi. I can just invoke pi, and it'll be there. I've already also touched on our support for entity and value types. Here you can see examples of how we declare those. Okay, so recall that entity and value types are central and key for our support of this graph normal form, right? So taking data that lacks any sort of semantic understanding around it and really making it a thing. Okay, so annotating it in a way that indicates what that data represents. Okay. Um, we can support through value types abstract user defined data types essentially. So here is an example with a definition of hour and minute. Okay, so I have some declaration that an hour has to be an integer and it has to be within this range. And then if I pass in any integer that qualifies that's an integer and it is within this range, then it'll give me back out that number, but as an hour type. Okay, so hour 4, hour 6, and so on. Similarly with minutes, right? And now I can construct higher order sort of date time relations, which is always fun to support date times thoroughly. So now I can construct a sense of a time as an hour and a minute, for instance, or a time interval, which is takes in 2 different times. Okay, and I can build these things on top of each other. Um, Entity types are a similar tool in the sense that they allow you to construct these sort of unique keys, but entity types are actually all have a value type that's all hashes, right? So it allows you to pass in a unique set of data and get out like a single element that's going to be a unique identifier and is a deterministic unique identifier. Okay. And I think I showed you a visual example of that before with the flights. So these two together really enable a very expressive ontology and encoding of semantic meaning in our data, and they really make that GNF idea possible. Um, we also support specialization. So you actually already saw a bit of an example of this with the pi. Um, we can take a relation and we can turn data into schema. Okay, so here, what you saw before was an example of how we overload relations. So here I'm going to show you how you can construct that yourself with constructing your own specialized data. So here we have a sort of fun example about platforms, train platforms, and who are allowed on the train platforms. So, for example, we could take the string and specialize it into a type. So platform 1A is muggles. We have an integer here, platform 2, muggles. And here we have a sort of actually an algebraic expression here, 9 plus 3/4. And this one allows wizards and witches. It's a very practical example here. And we see if we look at the physical representation, we've actually created 3 relations, right? So we've specialized these values, and now we have a relation 1A, a relation that's an integer type, right? And a relation that's this float type. But these are now schema. They're saved as schema really in our database rather than as data, which is important for how we actually query over it under the hood. Okay. All right. So yeah. So here you're saying that you have this type 1A, this relation 1A, and then a string, that's the muggles, and then this special relation 2 and the special relation that's a float. We also support, oh, Stefan, you've joined us. Hey, I've bled into his part of the talk because he had to step out to take our children to school. It's actually bright and early for us here in the US. Did you want to start taking over, Stefan? Are you ready?
No, I mean it's 2 more slides and then probably take a break and then I'll.
That
Yeah.
sounds great. Let's organize it that way then. All right. So I'm just going to finish up on the language key aspects. So um, another thing we support is native transaction control. So using relations instead of keywords and being able to entangle application logic with transaction logic. So you can really do a lot of your transaction logic also in database. So what is an example of that? What does that mean? So for instance, let's say I want to insert into a log, and I want to insert some timestamp, some sort of label, and a value. I can actually write that in database. I can and then uh, yeah, so then I can sorry, I can write that in the database and do an insert. And you can see here I even have I've used insert in the definition of this value, or sorry, of this log value. And then here with the def output, I can query that as well in the same transaction. We can also do reflective modeling. So here we have an example of self-modifying logic. You can write rel in rel and then install it. So you can write your logic with rel and then install it as logic and have it execute. Okay, so this enables some fairly novel package management and some really dynamic uh, uh, model development. Okay, it's also a good tool for code introspection, and it makes rel very extensible. So let me just show you a kind of trivial example of that. All of our models are installed, okay, and then they are updated on top of the data incrementally. Okay, so and they all have some sort of name associated with them. So here I'm defining a model. I'm calling it model 1, and I'm writing as a string some rel code. So here, the definition of the relation foo is just has the value 1. Okay. I can do that. I can do an insert into the rel catalog of this model, and then I can query it. Right. So now I'm querying in the same transaction again the output of foo, and I'll see that it's 1. I'll get my data back out. So you can imagine, this is a quite trivial example, but you can imagine using your application data to construct relations that you then install as well. So you can have this self-modifying behavior. So, summarizing, there's a lot covered here. Okay, so but I hope you can see why supporting all of these various features really required us to step back and really do this from first principles, right? Really come back and create a new language. We've gone we have as our roots sort of this data log idea. Of first order logic, but we've really gone beyond that to support fully featured applications and really being able to construct them in database and support them and query them and so on. So we support relational logic. It's all declarative logic. We support higher order logic. We support recursion and including non-monotonic recursion, including aggregations, including negation. We support abstraction. We support schema abstraction and schemaless modeling. You've seen we support modules and this sort of capability to use to access schema and data really on the same level. We support integrity constraints. We support entity and value types and these key ingredients for doing the graph normal form. We support specialization. We support, so turning data into schema, that's specialization, turning data into schema. We support native transaction control, and we support reflective modeling. So maybe now is the time to take a pause, Stefan. What do you think? I think so.
We go. So the second part of the talk will be a little bit more application focused. So there will be a little bit more examples and so on, and trying to see a little bit more of our system now and well in action. And yeah, now a big focus will be on really what you have seen so far, what with all the key features that it all has, and seeing how they actually play out and how they make things actually quite nice to express. So, but of course, we also since we are like a company and we want to attract a lot of people, and we also were like declarative languages or data log type of languages are not like the most commonplace language, and most people, right, they SQL, Python, and so on. And so in that way, we want to make it for these people also easy to use our system and maybe get a flavor for it, and then they see like, oh, that is cool, and then slowly like nudge them, and hey, if you want to do more than SQL, then you can also learn well, but you don't really have to if you don't need to, especially again, like some of our key users are maybe BI people that want to just build some aggregation about some data that the data engineers and data scientists like develop, and just to build up some platforms and data tools. So in that respect, we're also actively working on building a layer or like a connection layer with SQL, where we actually and that we do in close collaboration with DuckDB. So it's really like what they're doing. And so we're basically using DuckDB and their SQL support, and basically now translating the SQL queries that they have and so on in well relations and well queries, and then send them to our system. And so they are also more and more like planning also to support like like views and so on, and really trying to, our goal is that to really fully cover to support the entire querying specs of the SQL language. So and that respect, you can, if people want to use us, maybe not because of the expressiveness, but maybe more like for um, so some of the data logic or the data querying part, or or people just and on top of it want to kind of choose it as a normal database, they could, and then they could potentially like here write this normal select statement, like give me the order key, customer order date from order where the total price is larger than 100, and we would automatically translate this in what it would mean in val. And here you see again, because that is the as the data when we capture it or organize it, we organize it in this graph normal form, so we're extremely flexible. And if you know, if you take talking about SQL table, then we have here this module that is kind of your SQL table name, and then each column in the SQL table is its own relation that has its key. Here the key is its own for like order ID and so on. And then we can also write some derived rules, for instance, like total price here, for instance, is maybe not a column in your original data, but you can, in our system, easily just could add this, and you see it's the sum over the charge and so on, and then you could just create it out, and we can very easily like express the SQL queries with group by and everything in our language. So, but now let's get back to RHEL, because that's what we are here a little bit trying to focus on, and also what we really can now express with it, what we can do with it. And before going about the query optimization aspect, how everything kind of planning to make it work and performance, so that it actually also runs and gives you a nice experience. So let's go back to our so we'll go to example with the FFA flight example. So here again, like what an intelligent data app could look like is, for instance, you have your flight network where you have various flights in the US, and you want to track them, and maybe you want to build some kind of some dashboard for regulators, for customers, for the airline um, administration, or for the carriers that they want to analyze the performance of the network. So there are various types of reasons why you want to how you could build like intelligent data app on top of this flight data. And you can ask for various things that you potentially want to look at. Is you want to look at how how planes are like delayed by season, by the day of time, by weather, by areas, by an airport, like how for instance Alaska or the Northeast compares, so, and how they fluctuate. And so you kind of can basically gain some insights from how they behave, and in that respect kind of like plan ahead, and then do like better planning. And ideally, even what we're also working on, we'll see like in the last part of our talk, is that we're also more and more trying to implement and support optimization techniques that can actually express mathematical optimization, like a linear programming, so on, in RHEL. and to potentially like optimize certain aspects you want to improve. And of course, you looking at historical trends and so on is a classic thing you want to do. And another thing is, of course, flights happening all the time. There's, I guess, every given moment, there's at least one airplane in the sky flying from one airport to another. So the app in general should be also like live reactive, right? You have always data gets updated, gets added, and so on. So all this logic also you kind of want to maintain to make sure if you query it that it's like reflects the latest status. And so going back to all the key aspects, basically this example, and we were talking about it a little bit again, and basically touches on these key aspects in RHEL that we make use of to make it work. So right, you will see like right, we again using the relational data model and relational language, we use declarative logic, how we express our application logic, use higher order logic because again, here we talk about graphs and networks, and so they are naturally like you very fast end up writing higher order stuff, also with recursion, like you want to find shortest paths and so on. And we make also use of abstraction, schema abstraction, and so on. And so you will see that go through the slide. So again, here, this is what you've already seen in the first part of the talk, how our data roughly looks like, right? We have this big white table with carriers and so on, and here flight times, flight delays, and so on. And this idea, the first thing that you wanted to do is to model again what is the meaning of the data. And Cassie covered it already quite a bit, so I'm not like repeating it too much again here. So, but there is this idea again, like what does delay mean? What does transfer mean? And so on. So we really want to define that. So then if you build like really apps on top of the database, that they all have the same definition, right? Especially with delays, you can think about delays as maybe in feels like it's a trivial definition of what a delay is, right? You have the delay column here, and you just take this data. But as we said, so there's in real world, there's always a lot of subtlety to these data points. Is what does negative delays mean? What does zero mean? Does zero mean really it's on time? Or you see here, if a flight was canceled, it also has a zero delay. So in that way, like, so you have to be very careful what you do there, or if you really have CSV data over SQL and potentially have the null. And so they have a lot of these like small corner cases that maybe at the very beginning in the vanilla case you don't think about, that you want to really track and want to make sure that across your system you have like a uniform definition what it means. So that way, if you build multiple apps or stuff, that you actually always get the same answer. And of course, you also want to like that they're also based on the same data too. And and so there again, here we built this conceptual model where we really, for instance, also can define what is a heliport, for instance. Heliport is, for instance, if you say it's an airport that has as a fact type heliport. Or a canceled flight is what where we defined earlier, like an entity type of flight, and it has kind of an attribute where in the canceled attribute is a y, and so on. And in the case, I'll talk about here the survival delay and so on. So we can define and again, we make here use of what is a, we can really also define our own coordinate system, right? If your system in Valve, since we have this expressive logic, if you need new data type or something to express something more concisely, you can just create it yourself. For instance, here we can create coordinates where we say like, oh, where's an airport? An airport basically is a value type. This is longitude, latitude, and I guess angle or elevation, and you see you basically provide these three data points to it, and here you see how this value type is generated. It's a triplet with 2 degrees for longitude and altitude, and then length is kind of like gives you the height, and we see like the height effectively needs to be given in feet, meters, or miles, but also because length itself is a value type, we know exactly now if you provide 10, we also provide like what units we have, so that we know exactly what we're talking about. Um, and so this is here our data model. You can of this flight application, how you can visualize it. And for a visualization tool, we really love the ORM modeling diagrams. ORM stands for object role modeling. So because ORM goes beyond what normally you see with label property graphs, where normally you just have nodes of your graph, and then you have a connected, and then you have the name of the edges. For instance, this is like, it's located in, or so on, and then normally in the node you have your properties. But in ORM, and what fits really nice to our relational modeling is, again, everything is a relation, and we have nodes. Nodes are effectively unary relation that just have, like, if it's an entity, contain all the entity keys or hashes, for instance, of flights and aircrafts. Then they can have properties. Your properties, you see, they're kind of like these dash boxes, like, have flight time, basically is of unit minutes. And then also we have various different datetime properties, like actual departure, actual arrival, and so on. And the nice thing in OM, you can model this, and on top of this, you can not just model their connection, what it means, but you can also give them some much more some domain knowledge, and some really some constraints about it. For instance, there's constraints. If you have a bar on top of it, it kind of means the value has to be unique. So you can define, is this relation, is it a one-to-one map? Is it one-to-many? Is it a many-to-many? So that, for instance, has like big implications, especially if you give it to the query optimizer, because if the query optimizer knows that, this is a one-to-one map, then, it doesn't need to re-index that relation, and it just can really use it as is, or easily can transpose it, and so on. And the nice thing in ORM allows you to express it on top of the overall, like, schema and connectivity. And then you can even express, like, really complex constraints. For instance, up here, this little circle there is an XOR constraint, that you say a flight is basically arrived, is canceled, or is diverted. So it's one of them. And so now these all models, we can now very nicely, also seeing here visually, we can very easily translate into REL what they mean. And in REL, again, now we can make use of our integrity constraints that we have. We can express them very nicely. And we even have tools that automatically go from, if you just model this, they automatically can even generate you these integrity constraints. And for instance, here we can then say, like, all the nodes of the relation, for instance, all edge relations origin that connect, like, a flight with an airport, basically means that this edge origin needs to connect a flight with an airport, where the first entry is a flight, and your second argument here is an airport. Then, of course, you can also have some requirement statements. You can say, for instance, if you have a flight, every flight needs to have an origin. So it needs to start somewhere. So that way here you can, like, express these, like, explicit, like, logical constraint. And then you can go even further and say something here, for instance, function origin. And function effectively means it's a functional dependence. So that means that if you know a flight F, you can from that relation origin infer from which airport it started. So this basically, this function enforces here that this edge is a one-to-one map. So once you have a flight, it only has one, or or at least a one-to-many. It can only start from one airport. It's not a one-to-one, because from an airport, multiple flights can start. But so all these things we can very nicely express, and then we can here further go express as complex of a logic as we want. So we can here, for instance, say if a flight is a canceled flight, then that means there should be no flight duration. So because the flight was canceled. So that we can really clearly say, like, if data comes in, we can really ensure that the database stays clean, and that we not kind of, like, somehow at a later point, data comes in and said, oh, it's a canceled flight, but maybe accidentally the flight duration was positive and we just kept it. So if we have this integrity constraint and we really install this in our database system makes sure that this fact is always true. And then here, similarly, you can say, like, if you have a flight, it's here, again, what we saw before in the OHM diagram is effectively this here is the corresponding integrity constraint. Every flight, for every flight in our relation flight, it's canceled, it's diverted, or it's arrived. And it has to be an XOR. So it cannot be canceled and arrived, and so on. And if you would enter a data point that violates this, then like our system would say like this is not allowed, and for instance, it would prohibit us from entering this dirty or data that is inconsistent with our modeling logic. And so this is really what we feel like is makes our semantic layer and our data really like powerful, that we can define this and we define it in the database with the data, and now you can just connect your applications on top of it, whatever it is, and basically then you just like query these relations, and if you want you can query them almost like SQL tables, but under the hood all these kind of integrity constraints and dependencies, they're all like fulfilled and they hold. And of course, since we are declarative language, we can do all the standard also aggregations, right? We can just count flights, then we get the number of all the flights in our data set. Also, what is really cool and well is you can express group by aggregations in a really nice way. Is it's basically here for every carrier, we count all the flights that's operated by that carrier. So we take this edge operated by that connects the flight to the carrier, but now we do a group by, so it means for every C here, we count the corresponding F's flights in for the carrier. And so basically now we're calculating how many flights it's used carrier. And here you see the answer on the right side. With Southwest, Delta, and America roughly being all over 4 million flights. And then we can, of course, go even further and also can ask what is the mean arrival time for each carrier. Again, here we have our group by. Now we do a mean instead of the count. The mean, again, I guess we showed before, through our higher order abstraction, effectively just under the hood, then translate into a sum and a count. And then ideally gets optimized accordingly. And here again, we say within the mean, let's go over every flight for a given carrier C. And now for that flight, give us the arrival date, and then and that set give us the mean base for each carrier. And then here we see the worst airline with the largest delays are like AirTran and Atlantic Coast. So they're defunct. They don't exist anymore. They're bankrupt. So I guess now we know why. And then the next one is then United. And apparently the best performance airline is Hawaiian Airline. So so it's good to know. And of course, again, similar theme again, we can make these logic as complicated as we want, and through these like abstraction and so on, we can really write this logic, write them somewhere else, have this definition as higher order place that you can just reuse. And for instance, you can define something like a ratio, and here you can just provide then these two data sets about canceled flights and the arriving flights, and then and this ratio relation here would then tell us for each airport, for instance, what is the ratio of canceled flight versus flights that arrive. And here we see, for instance, the airport in Alaska is almost like 20% of the total flights they have are canceled. So it seems like they struggle a lot with weather and so on. And so this is kind of the insights you can do, and you can again then define them as new derived relations, effectively very similar like fuse in SQL, and then on your app you just then only call that type of view, and then you can just display it as you want to. And of course, in RHEL, you already have seen we can do more and more also reasoning aspect that goes beyond just aggregation, right? You can do very naturally, you can express recursive and transitive closure. So in the key feature section, you saw something transitive closure like the reachable, and in this pointless form where you don't explicitly write out your parameters. So here it's a little bit more explicit, and we can have something very similar here, like with located in, X is located in Y. If X is located in it, there exists a T where X is located in and T is located in a Y. So of course then so this is again something again that is very, very natural and transitive, and you can express this, and this way you can now even express it. You can express it as an integrity constraint if you want to check something. But here, for instance, we actually use it for creating new value or new edges. So for instance, if your data set only talks is the neighboring one, let's say like if you say a city is located in a state, and then you only have a separate statement that state is located in this country, like in US, but you don't need to explicitly have the data point that that city is located in US. You can through logic like this, you can automatically infer this. And now in your data app, that inferred logic, that new statements basically coexist with your original data that you just imported as CSV data. And so for you as the end user, then these two types of data, these base relation, or like EDBs, and this derived relation, that are kind of these views, or IDBs, basically feel very much the same for you. And then here you see we can do that also very channel concept. For instance, here we can define what is an airport distance. An airport distance between two airports, AP1, AP2. So you see here we can nicely say that there should be airports, and then we calculate, like, then here we define the distance between the coordinates of the corresponding airports. And then how is distance defined? So distance we define down here, and then we say distance is between two like coordinates, and the coordinates have to be in this LL value type that we saw before. And these are then used and provided into the Heaviside function that, again, you can also define in val fully. And then here you provide as a parameter the Earth radius, because of Earth. And then you see here via this radius is provided also in kilometers. So you see we really neatly track what units we're using, that we're not like confusing and at one point using kilometers and we use miles and so on. And yeah, and then also, because we are having this visualization, what you saw in the past with relations, we can do very similar here. We have these relations that almost feel like operations, that kind of act on two operators, or on two values, and produce a third value, and so on. And then we can also overlay. We can have distance here. For instance, here they are based on this longitude latitude aspects. You can have then a separate distance relation that basically operates just on heights, on length, on depths, on time, and so on. And they basically are coexist next to each other, and they would not interfere. And basically our front end and compiler, just based on knowing, then inferring the data types of your data, would then specialize which kind of under the hood actually function and operation are executed. And here again, and down here, there's another example, for instance, around transfer counts, because how often you need to transfer to go from airport AP1 to airport AP2 with a given carrier C. And so here now we can just again give this information to another relation that ideally, like in the future, we will have in our graph library. So it's just a library relation that you just can use. Of course, you can also write it yourself, but we have more and more will have libraries that you can just reuse them as you need. And here, for instance, then we just say like, oh, give us all the routes for a given carrier. And then we kind of conditions like, oh, and then I want the shortest path lengths between these specific airports. And you see a little bit later when you talk about query optimization, about actually how the shortest path length is implemented. This is, for instance, again, like a recursive query. And then what is also very neat, what we can do again with the schema abstraction. And you see here this val code looks very much the same that I showed you before, but it is a tick different, because actually node label here is schema information. So this is actually could be a relational name for like the flight graph is our module that basically contains the entire graph data, the entire knowledge graph. And now the node label is effectively the type of nodes you have. For instance, you have a flight, you have an airport, right? You have a city, and so on. So and they are all under the hood separate relations. And here we can count them and say, like, give us for every node type or node label, and then count all the IDs in that label. And so you effectively get the count of all the nodes. So, but what we can also do is, again, we can do nice group by queries, and now we can do group by queries over the schema and the data and intermingled. And here we say, for instance, for each node label, now count how many nodes we have. And there we see, like, we have, for instance, over 37 million flight nodes. We have around 360,000 aircraft nodes, and so on. And you can really express them here. Now and here, as you see, it's really cool how we express the schema data and the actual data in the same way. So effectively in the val code, you could, if you write it like this and you don't explicitly here state what what the type of the variables have to be, you basically you have no idea if it goes over schema or over data. And and this is actually really cool, and you can push it even further. That means you can also use the same logic to not just create a graph representation of the data itself, that you say, like, you can fly from LA to Boston or something, and then you have a node, but you can also do it over the schema. So you can build a schema graph. So you say, like, oh, what concepts are connected with what? So that's basically what you saw earlier also with the ORM diagram. But here now we can generate that in rel by itself. And here you see again, you can define here the schema graph module. So we have a module that now acts almost like a transformer, where we provide a graph G, that G has now all our nodes and all our all the types, like with the aircraft and the airports and so on. And now we say, like, just give us a very simple graph that where we strip all the label nodes, and we just collect, we collect nodes and edges. And here we give me all the node, um, and we here take that X. The X is again is the node label. So all the nodes are now the node label, the relational names effectively. And then down here on the edge, we say, now give me all the edge names, but then, like, connect not the explicit data to each other, but connect what node types are connected. So in that way, we see um, on the left, you see and then we can give that, for instance, to a visualization library like Graphis, and we can plot this, and this is the result you see on the left. And there you see, for instance, flights are connected in your schema to carrier, to aircraft, to airports, and so on. And you see also through which edge connections. And again, now this logic, you basically can you can take this module and you can apply it now to every graph that you want. And it's basically very universal. And that's what we more and more now are planning to do, to package them up in libraries and then make them available so that people just can use them and don't always need to reinvent the wheels. But the cool thing is, as you see here, you can fully write them in rel. You don't need to have some special keywords to say, oh, now I want to query over the schema or over the data and so on. And then you can do cool stuff, like also your recursion can now go over the schema. So you don't need to have recursion over the data, but now, since the schema feels like data, you can do the same shortest path calculation over your schema, and you could say, oh, give me all the shortest paths between flights and states. So how do you get from flight to states? And then you see here, flight is up here, state is down here. So flights are connected to airports through origin destination, and airports are located in state. But and so this is basically the shortest path. And so up here you see have twice, so you have two options. But now you can also say, oh, just give me all paths. I don't care if it's the shortest or not. And then you see, we can actually see here how we go also look it down, and we go from flight to airport to city and state, or from flight to airport, city, county, and then state. And all these options down here you automatically get. So and yeah, and it's really cool. So you can really just write the same logic. Actually, this acyclic graph you can write. It doesn't need to be written for the schema. You just write it generically, and then just your front end compiler knows, based on the data type that it infers under the hood, what to do. And yeah, and then, for instance, here's just a little visual example around again, where we applied to that data set PageRank in the shortest path, and where the PageRank is based on is applied to the airports, and then the shortest path, for instance, between two different airports, and it's highlighted here. And the PageRank algorithm you already saw, like earlier in the first part that Cassie presented, the shortest path you will see in a moment. But there, I think just for complexity, we show, I think, the shortest path lengths only, and not the actual how we generate the path. But again, this is also, like, where it comes to shortest path, you would really need value creation, because each path is basically a path of a subpath and an extra step. So you really also recursively create new concepts and entity types, and so or entities. And yeah, so in that way, this is a really powerful, all the features we have to make all this work. And this also allows us really to keep everything in the database, and really there should be no need really that you need to go to Java or Python and so on to express these things. So how does it work? So why can we do all this in a database? And one of the key answers is because of query optimization. So we have a really good query optimizer, not just optimizes like simple joins or like and so on. But it really optimizes like your entire logic, and it also can optimize cross aggregation and joins and how they interplay. And so this is really also one of our key innovations around semantic optimization. And and there the high level view of where the semantic optimizer sit is that you have your rel model, but you also have some knowledge that, for instance, you can express through integrity constraints that you can say like, oh, here this relation has a functional dependence or is a one-to-one map. So, and then the semantic optimizer takes a rel model, takes all the knowledge also you explicitly define, and then trying to find equivalent, semantically equivalent val expressions that basically calculates the same thing and analyzes what is the most efficient way to calculate it. Then it spits out this optimized code and then calculates the answer and gives you the answer back. Um, and 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 how the semantic optimizer works, it basically uses like certain types of general constraint. Often a lot of these logic that's written are around like semi-rings and so on. Um, and there like you make use of, for instance, if you know plus is commutative, x plus y is y plus x, and so on. The same for multiplication. Is you have associativity, you know you have the identity for multiplication is 1, for plus is 0, and so on, and also how infinity works. So you really make a lot of use of just like mathematical properties. Then of course what you have with the maximal axioms, then also from technical you make use of these functional dependence that you know that the user can define as domain knowledge. And then of course also the optimizer will make use of summary and statistic histogram. So it will analyze, it knows certain relation, it knows the basic statistic like what is the size and so on, and that it can estimate like, oh, like when it comes to join orders and so on, like how big are the loops, and roughly makes a best guess estimate, and ideally even over time learns this how it's better and better, and at the end gives you the optimal query plan. And so here's just one little example. Is for instance the semantic optimizer, how it works for minimization is if you minimize like the sum of f plus g, and you see f is indexed by I, g by j, but you see there are two different indices, so they're actually independent. So actually optimizer will know you can just calculate the minimum of f and then the minimum of g, and then we just add the minimum. So, but then it knows, oh, if it's the same index, we cannot separate them. So this is kind of what you talk about, this math axioms, that it knows it can like push this aggregation through the joins and so on, if it's possible or not. And for instance, for plus, it's not. Here for count and multiplication, you can. Also, it does really cool stuff like here, if we join something between R and S, but you start like here X and Y, they have to be different. So normally, if you would not have that last statement, the count would be again independent and you could split it apart, but because they have to here, because X and Y have to be different, so they become correlated. And the optimizer knows that actually I can rewrite this into something that where I have no, that just have a one. So basically I allow everything, so I don't make no condition, and then just subtract the cases where x is equal y. And now you can in this way like rewrite this discount query into something here where it factorizes, and then you just subtract something uh, over a relation that is much shorter, and you can potentially get much faster can evaluate. So and very similarly, you can do the same with if you know talk about recursion. So how we can optimize recursions and aggregations. You see here, if you have a path, it's an edge between x and y, and then you define path recursively between x and y if a path is from x to t, and then there's an edge from t to y. And then you can, for instance, say shortest path length is just the minimum of the path. So of the length, and then the optimizer will know, it knows how minimization and addition works, that you can like push the disaggregation into the sum, and you can actually do vice versa, that you have here outside the minimum, and then here you have the join statement between the edge and the shortest path links here inside. And you see this is again a recursive query that has aggregation, so it's an unsatisfied, and again, so for graph queries, these kind of like patterns show up all the time. And so that's the reason why for us it's really key to have this non-satisfied recursive capabilities. And yeah, and here's a bunch of papers that by Hung and Co. that really pushed this, and there are various parts paper with best paper awards, so and so on. So there, yeah. So what the team is doing there, our semantic query optimizer team, it's like really state of the art, and it's and all this knowledge that they're really trying to that they implement in our system. So and this is why we're thinking our system can do this, and we can really optimize these complex programs in our system with our query optimizer, and there's no need for us to go to a procedural language like Java and so on. There's of course also something about
I wanted to time check you here,
yeah.
Stefan. Maybe we should skip the incremental conversation if we want to get to the fun probabilistic stuff that you
Yeah.
have in store.
Yeah, good point. Yeah, let me just stop here. So also, just very quick, so we can also do, again, for a lot of this live program is incremental maintenance. And so there the idea is if your database changes, also your views on the database get automatically maintained, and ideally they get maintained in a way that is like minimal. So so that way if you have some rolling sum or so ever, you don't need to recommute everything just because you add one more data point, and ideally you can your your update is proportional to the size of your data change and not proportional to the size of your data. And of course, the idea is we're also trying to make this incremental maintenance work with inversion and so on. So as well that even recursion that we're trying to only like recalculate as minimal as we need to. And yeah, we don't have time for this. And so again, there are also again key papers and so on and from our team that looked into this. So now maybe what is a little bit um, also along the whole theme of the workshop is about trying to make it really intelligent and also really come up with a not just like descriptive reasoning, like where you have hard rules, but also predictive reasoning, getting machine learning and optimization really into the database and probabilistic modeling. And so this is something that is still like really part of them more and more slowly getting into production, like mathematical optimization and relational ML. We are further apart than, for instance, when it comes to simulation and probabilistic modeling is where we eventually want to be, but right now we're still more on exploratory phase and see what we can do there in our system. And maybe let me go here a little bit further. So in general, I think there are two key ways how you can bring really this predictive reasoning into a database. So one approach is you just bind to external packages like XGBoost, MLPack, maybe TensorFlow, and so on. So that way, the nice thing is you can really just make use of these specialized function packages, and you don't need to reinvent the wheel. And we have done that to some extent, as you see, especially with XGBoost and MLPack. But what we are really trying to push is that you really can write your whole machine learning model in RHEL and in RHEL itself completely. And so this will give you some unique optimization and speed up possibilities where really, again, the query optimizer can optimizes your whole data model, including your machine learning model. It can also express relationally and trying to find out the best way to calculate it and automatically identify like independence, for instance, and then just factorize it out. So you don't need to necessarily need to create big data in between. And one aspect that now I want to focus on more in this section is around simulation and probabilistic models. So a little bit where we there want to go. So this is more something that's more aspirational. So, but for instance, we know data is real world data, or the real world has a lot of uncertainty and noise. So it's not just always a straight line. And generally, like, if you think about what is expert knowledge is normally you do a best guess. There is some person with the domain and just kind of finds the best model with like and he defines the parameters, and that's a parameter you use. Then in the second wave is kind of where we do this data-driven optimization, like with maximum likelihood estimate and so on, where you really just based on the data, you're trying to minimize the error and then find the best fit. And but again, so the parameters are normally just one value. And now if you go to probabilistic modeling, the idea is you really like say acknowledge the uncertainty and there you're trying to model uncertainty within your model and keep it in your model. And you say here, your slope C is not just a value, it's actually a distribution. And this distribution is now for instance, is a normal distribution with a mean and a variation. And of course, this is something you really want to do, especially if your distributions are non-Gaussian or non-normal. If it's Gaussian, normally that works really well. But for instance, if you have non-Gaussian or more and more these like multimodal distribution, then just having one value is less and less if optimal to actually describe your system or the world that you want to describe. And so that's where also simulation comes into a database where we want to um, really put that in so that we can handle this kind of situation and build like intelligent reasoning logic on top of it. And in that respect, also, what is simulation? Simulation is effectively a way how you want to compute all the possible outcomes, or you want to calculate the possible outcomes of a probabilistic model. And the probabilistic model is basically just a logical model with random variables. And there are some key requirements for us to make these probabilistic models work, because again, we have the query optimizer, we have this incremental view maintenance and so on. And so we don't want to give up on all that stuff to doing simulation, but this requires some key properties for us that this probabilistic model needs to fulfill. For instance, you need to always get the same value out regardless of reevaluating the same thing twice, because again, you don't know if it's in a recursive loop, so you're trying to find a fixed point. You don't know how often it gets reevaluated. It needs to be, the value that you get back needs to be stable. Also, execution reordering should not impact the outcome, and this is key because if we run our query optimizer over it, it maybe rearranges how it gets evaluated. And of course, if it next time somehow finds some different path because you added something, it gets completely a different result. That also makes it then not very performance. And so there we found what is really for us works well is there's certain pseudo random generators like especially like counter-based yeah, like counter-based PNG like 3-phi that where the state of your random number generator more splits like a tree, and with this way you can really mimic the whole like model or logical your probabilistic model that you're writing, and you can really split like along these lines, where if you have a serial pseudo number generator, is then like every time you call it, it goes to the next step. So but then it becomes really hard to, if you relate something twice, but now your state is your PNG is in a different state, so you have a different value, and this of course destroys then all the good properties of our database. Yeah, so then here are a few little examples. So is, for instance, we could throw a die, and how would that works? Like if you're trying to throw a dice multiple times, you would just say, hey, let's have something uniform. A key here is effectively the seed that we would use, and then just give me a number between 1 and 6. And that seed here is our key. And then we say like output this for this die, where we just now iterate over that key from 1 to 5. So this is effectively our throw ID, what is first experiment, second experiment, and so on. And this here on the second column is effectively the outcome. So we can do, of course, then build up on there and say, for instance, let's throw n dice depending on the value n of the first dice. So this is now something where you have now some variable logic that depend random variables depend on the outcome of a first random variable. And this again we can express now very nicely in rel as well. So for instance, here you see our multiple dice here. Here in the second line is basically a dice that gets a new key that basically comes that key, it branches it off with an index from I to the number of the face value of the first die. This is the die key. So if this one is 5, then I goes from 1 to 5, and then we take this key and we split it 5 times in different and then we get 5 different keys again, and then we apply them to die again. So we basically get then 5 different outcomes, and then we repeat that up here. We do that 3 times. So 3 times we throw the first dice, and then depending on the face value of that first dice, we throw 3, 5, 4 dice, and so on. And here on the right side, you see the outcome. You see that in the first experiment, there's only 2 ones. So it basically means we had a 2, and then we threw 2 dice. In the second time, we threw like 1, 2, 3, 5 dice. So we got the 5 in the first, and so on. And so this is now, you see here, but also with this abstraction that we have in Valve, we can express this kind of like logic really compactly and actually quite intuitively. And yeah, and then basically you can go a step further. Now you can view each of these experiments as basically a realization of a possible world, and a possible world is basically also something realization of your probabilistic model. And what is a probabilistic model and database? Basically something like a probabilistic database. So now we basically can that way generate multiple possible database states of your probabilistic database, and now we can do reasoning on top of it. So for instance, we can calculate something, give me the variance of the mean of each data set. So we take here our data set I, this is the basically the I index our possible worlds, calculate the mean for each world, and then take the standard deviation across the worlds. Or something like with our dices, given what is the mean sum of each data set. So here we can calculate the sum for each dice. One time we just sum up 2 dice, sometimes we sum up 4 dice, and so on. And then we can take the mean of this, and you see in roughly the mean would be 12 that you get on with, if you count all the faces up. And yeah, but then if you want to do, of course, more and you now add observations to it. So normally what you want to do now, you need to start also adding rejection to all the sampling, because you ideally want to only keep worlds that are in accordance with the real world that you observed in the past. And I'm not sure how much time you have, but effectively maybe you just take three more minutes and a little slow fast go over it. As so Vida, for instance, implemented an as a proof of principle. We kind of used the game Battleship. And so we said, hey, here we have the battleships, and let's see, like, what can we find the best strategy to find all the games of all the ships. And again, this is very much a simulation problem. And then you can use the simulation around realizing all these possible worlds, how the ships fit on your map, giving your all the moves you made in the past, right? There's no ship on A4, there is a ship on C5, and now you of course need to create all the worlds that are consistent with your observation, and of course are also consistent with the rules of the game, so that the ships, for instance, cannot overlap. And then you can count them, and based on this, like then, for instance, do an MLE and so on, and recommend the next move. And this here is, for instance, how we set up a shift. Even setting up the ships and putting ships on the board involves non-stratified recursion. You see here we're starting with the key where, because we want to put 5 ships on, and if they overlap, we need to put another 5 ships on till we find a valid configuration. And each time the configuration is not valid, we want to remove the ships and put new ships on. So that way also here we really have this negation in here. You see the nots and an empty and so on. And then, so what are the strategies you can have with Battleship? Of course, you can do just a simple one. You just randomly pick a place. That's of course not ideal. Then an improvement is, once you find one, you're trying to hunt down the chip. That's, I think, what everybody would do. And then of course you can have, well, with the probabilistic model, is you really try and give me observation. You're trying to give me all the possible now ship configurations are valid, and then you just count and look on which field you're most likely to find the ship. And here you kind of see what is the likelihood of these different strategies to win, where blue is the random, the green and red is the kind of like the hunt down, the other one is a little tweak, and then the orange one is the probabilistic one. And you see really how you're much early with much fewer moves, like 40 moves, you're able to find all the ships. With the hunt down, it's roughly around a little bit over 60, and if you do random, you almost basically need to find all the need to hit all the fields. And here, this is kind of a little bit the math, how you would set things up. So this is your configuration of valid ships. Then you would calculate here your conditional probabilities to find a ship at a position XY, giving an observation. And then normally you would do an argmax on top of it to give me like what field has the highest probability. And the one thing here I want to show last is these 3 math statements you can really nicely translate interval very easily. Here you say, what are your valid chip configurations? Effectively all the samples. The sample here is our sample ID. And since we have this higher order abstraction, you can really nicely say, like, oh, for this sample ID, give me all the chips. And now we have this condition, your chips non-overlapping. So basically analyze it for that chip configuration. Oh, all the chips not overlapping, and it's a valid configuration. And then of course you have the second condition. oh, also these ships need to be consistent with the observation we had so far. So you see again, we provide the ships, and then here the analyzed guess is effectively all the guess we had. We know here's a miss, here's a hit. Configurations we have need to be consistent. And then to calculate the likelihood, what we do is we now take these, we have all these samples that are valid, we count them, and we count all the valid examples. We do a group by X and Y, so basically we count all the valid samples for each field, and then we just divide them by the total count, so it gives us the probability of finding a ship on each field. And then here down here, we just now perform an argmax over it, and down here you see one thing that we exclude is, of course, we exclude the positions where we made a guess. If you know there is a ship there, of course the probability of finding a ship there is 100, but of course you don't want to guess the same field again. And so here's just some plots, both of them, so you can really generate in our system. You see first, you have no ships. You see the most best is to somehow look in the middle, and then as you find a hit, then you see like you kind of want to follow this hunt and target strategy, but there's some more subtlety to it. So effectively, it's more efficient if you do real probabilistic. And so we're also looking at some sample strategies. I'm not going into this. And we were looking in the future, we want to build some really higher order abstraction that we really much more more intuitively and for users that can build these probabilistic models. But this is more something that we that will come into years to come. And so there are a lot of cool advantages like doing the simulation in the databases, right? You do the data generation in the database. The database is the best place to handle your data. You can also handle really naturally out of core, out of this data. So you can really naturally like simulate a lot and it scales, and you don't need to think about it as a user. And then of course at the same time, as your predictor reasoning is in the same place, now you have the query optimizer that optimizes the data generation and the analysis on top of it. And if, for instance, if it finds something is independent, it just like splits it apart, factorizes it, so it doesn't, so in that way it really minimizes data generation, data transfers, and so on. You don't need to move to a different system. It all stays on your same commute engine and so on. And yeah, and with this, that's kind of it. So just very briefly, maybe here, we're also right now working on providing, for instance, math optimization libraries that where you can write math optimization very much in RHEL the same way. And under the hood, then we give it to like an existing package, for instance, that does like linear or mixed integer programming and so on. And very similar, like also something with relational ML, but I don't think I have the time for this. And yeah, and with this, I think that concludes our talk is right. So effectively, the key message that we want to convey is what we are trying to build here, Relational AI, is a cloud-native relational database platform that is like designed for structured, semi-structured data like CSV, JSON, and so on, with data and application logic together in one place. And I hope we showed you guys why it's really like advantageous to have it at the same place, like with the query optimizer and so on, and showed you a few examples with the very flight example and so on, and showed you a little bit what we are currently working on and where we still wanted to go and push our system to when it comes to like simulation, probabilistic modeling, supporting optimization, and relational ML workloads. And this yeah, thank you for your attention.
Thanks a lot.